It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to lesson 9 here, where we're going to continue looking at linear and exponential functions. So let's start with this opening exercise here. Rachel and Mark were given the information shown below about bacteria growing in a petri dish in their biology class. Rachel wants to use a linear function, Mark wants to use exponential. Who's a better choice and why? So see how you do with this problem. Do we go with Rachel or do we go with Mark? Well, the key thing is that we need to understand that linear functions have to deal with a constant rate of change, repeated addition, whereas exponential functions are repeated multiplication. So it's easier to check, is it linear? It's easier to check, is there a constant rate of change? That's plus 60, that's plus 70, this isn't looking good, that's plus 90, I'm gonna quit right there. I'm gonna quit right there and say who's better? We're gonna go with Mark, since there isn't a constant rate of change. We're only linear if we have a constant rate of change. We're going to go with Mark, who said exponential, because there's not a constant rate of change. Because I don't have that constant rate of change, I'm not going to go with the exponential function. Alicia, she invented a new app for smartphones that 2 companies want to purchase from her. Company A is offering her $10,000 for the first month, and company B, will increase that by $5,000 a month. She gets $10,000 the first month, and then we keep on adding $5,000. Whereas company B, they offer her $500 a month, $500 for the first month, and then they're going to double it. So write me functions for A of n and B of n. So let's kind of figure this out here. The first month, she's getting $10,000. The next month, the second month, she's going to get $1,500. The third month, another, we keep adding. Adding means this is a linear function. So A of n here is linear. Well, that's y equals mx plus b. That's my rate. That's my way I write linear functions. My rate of change, what do I keep adding? I keep adding 5,000 n, but I need my y-intercept, so I've got to work backwards. I've got to always get back to my home base of 0. Instead of adding, we're going to end up subtracting. So I'm going to say a of n equals, and there's my linear function, 5,000 n plus 5,000. Whereas b had this doubling pattern. So b of n is going to be an exponential function. It's going to be an exponential function. They're only paying her $500. On month 1, she's getting 10,000. On month 1 over here, she's getting 500. The second month, though, it doubles. The next month, that doubles. The month after that, that doubles. So notice this is an exponential function because I have that repeated multiplication occurring there. So on day 0, how do I go backwards? Well, I need to divide to go backwards. So 250. So 250, I keep doubling it to the n power. Remember, exponential functions are a times b to the x. My starting amount and then my multiplier. Starting amount and then my multiplier. So clearly, company A is doing better, but does company B eventually wins. So let's look at a table here. I don't have my real calculator on here, so you guys have to deal with Desmos for a second. So I'm going to have I'm going to have to use x here. I'm going to use a of x just because I don't want to use n right now. A of x equals what was 5,000 x plus 5,000. And then b of x, my other function, so you would put this in y1 and then y2 on your calculators. And then b of x is equals, well, it was 250 parentheses 2 raised to the x power. So there's your exponential function. So what I want to do right now is I want to look at my table. So you're going to go to your table of values. And I'm going to let my calculator here, I want this column to be a of x. Sorry, I gotta put a 1 there. And I want this column to be b of x. B of x. I have a 1. Sorry, I'm just getting my table set up. So there we go. So now, month 0, it's going to tell me. Month 1, I should just be able to keep hitting enter right now, and it'll continue to generate this table for me. So I'm just going to keep hitting enter to keep generating this table. So notice over here that it starts off losing b of x. The exponential starts off losing, but as the table goes on here, eventually it starts to win. Where does it start to win? Right there at year 8. Look right here, it's 45, 64, 45, 64. So the winner is, when does it change? When will company B exceed company A? At month 8. Eventually, month 8 wins. Well, what if company B only started at $1? What if they only started at $1? So 1, 2. What if they only started at $1 there? Well, I got to go back to get my new, it's still doubling, but my new y-intercept is 0.05. If month 1 is $1, that changes my y-intercept here. Got to delete that out to be 50, not 0.05, sorry, just 0.5. 0.5. And look at the table. It starts off really slow. It starts off really slow. Let me add some more rows here. But eventually, it's an exponential function, so it's going to end up winning. That one wins. That one takes 18 months to win. Here's the thing. Exponential functions will always catch up. Exponential functions always catch up. Does it change my choice in the long run? No, it doesn't, because that doubling pattern is always going to outrun a slope. If I have a linear function, that's like a little engine that could, whereas an exponential might start off really slow, but once it starts growing, it skyrockets up. So eventually, an exponential curve will always be above a linear function. An exponential function will always win. Linear functions are repeated addition. Linear functions are repeated addition. Repeated addition. They're equal differences. There's equal differences I can subtract in the table. Whereas exponential functions, those are repeated multiplication right there. There's a huge difference between those. Those have a common factor. Those have an equal factor. Linear functions have an equal difference. Exponential functions have that equal factor, that number I keep multiplying by. So what can we say about an increasing exponential function compared to an increasing linear function? Eventually, it might take a while to get there. Eventually, the exponential function will exceed the linear function. Every time, no matter how fast it grows, I will always be able to find some point where the exponential curve wins. Exponential functions grow the fastest. What type of, out of all the functions we deal with in Algebra 1, even stuff we haven't learned yet, exponential functions are the functions that grow the fastest. And then I've got these points here, 0, 4, and 1, 2. So I got 2 points there. Let's look at that. Let's graph those 2 points. Let me get rid of all this. So I've got the points 0, 4, and the points 1, 12. So I've got 2 points there. There they are. I got 0, 4, and 1, 12. Write the equation of the linear function. So linear function is y equals mx plus b. So in a table here, I'm looking for an additive pattern. Well, I add 8 per 1. So that gives me a slope of 8 over 1. I have a slope of 8. 8 is the number I keep adding. That's my constant rate of change. So this would be the equation y equals 8x plus my starting point of 4. So that equation there, 8x plus 4, y equals 8x plus 4 is the equation of the line that passes through those 2 points, as we see there. But let's take that same table now and think about it in terms of a multiplicative relationship, in terms of multiplying, in terms of an exponential function. What's my multiplier here? Well, my multiplier is times 3. So this is the form of y equals ab to the x, right? Y equals the starting amount times the multiplier to the x, that repeated multiplier to the x power. So here, my starting amount is 4, just like it was in the linear function, but I'm doing repeated times 3 to the x. So 4 times 3 to the x is this function, y equals 4 times 3 to the x. And we'll see that blue curve there also passes through those exact same points. You'll see that blue curve there also passes, let me fix the scaling here just to make it a little nicer on our eyes so we can kind of see it. Still not great. There we go. So I have my 2 points there, 0, 4, and 112. And notice between any 2 points, I can draw a line, but I could also draw an exponential function. And we'll end here with Pedro and Bobby and their ant farms. What a great way to end this unit. So Pedro and Bobby each own an ant farm. Pedro starts with 100 ants, that's important, and says his farm is growing exponentially at a rate of 15% each month. So Pedro over here, I'm going to say Pedro, let's write his equation. He's starting with 100 ants, and he's growing by 15%. So whenever I deal with a percentage, I turn it into a decimal, 0.15. And I never just use that decimal, I either do 1 plus or 1 minus for my multiplier. Since I'm growing, I'm going to do 1 plus. So 100, 1.05 to the t. His friend Bobby starts with 350 ants and says his is steadily decreasing by 5 ants each month. So Bobby over here, Bobby seems linear to me. Start at 350, minus 5, minus 5, minus 5, minus 5. So my rate of change is minus 5, and I'm starting at 350. How many months will they have about the same number of ants? So let's use a table. Let's use a table for these 2 equations that we made here. So go to y equals, or in this case I'm going to Desmos, go to y equals and we're going to type in, and y1, that's what I'll call this one y1. y1 equals 100 times 1.15 raised to the x. And in my y2, I'm going to type in, negative 5x plus 350. So those are my 2 functions, and now I want to make a table. I want to make a table for those functions there. y1 of x1. Sorry, I'm not going to use y1 actually. I'm going to change that to, what was that, p? That was Pedro. And then this was his friend Bobby. So I'm going to do, sorry, I'm using a different calculator than you, I know. I'm going to use p and b of x1. All right, so month 0, too many variables in defining x. All right, let's change it to like x3 then. Let me say p of x then. Is that what it wants? Does that make it happy? There we go. My fault. So Pedro started with 100, Bobby has 350. A month goes by, 2 months goes by. And we just keep letting the months go by, and in your table, you're going to scroll to see where are they about the same. I think it's around 8 months here, right? That's too far. The exponential kept growing, whereas the line was decreasing. And about here, around 8 months is where they crossed. Around 8 months. Why is it around 8 months? Well, at 8 months, Pedro's got how many ants? He's got 305.9, so about 306. And Bobby at 8 months has he has 310. So that's where they were about the same, around 8 months. So notice we can use our tables when we work with these linear and exponential functions.